So we have a mesh of sort, not refined completely, but a decent mesh. We have simplified the part to take advantage of symmetries and remove probably unnecessary pocket here. So now we are ready pretty much to simulate. So but what are we simulating? So what is this? Well, this is a conrod. So typically the conrod transmits power between the piston. So the piston there, so there's a pin here, and due to the cycle in the explosion engine that will move up and down and transmit power through the crankshaft. Here again, you probably notice that I have simplified here quite a lot. That very likely this should be cut. There should be some balls to join two halves of that head here. But so what are we simulating? Which loading are we going to apply here? And often choosing correct loading is actually a lot more difficult than it sounds. Sometimes the conditions or the boundary conditions are pretty obvious, but sometimes they are not so much. So depending at which stage in the cycle the piston or the conrod is going to be in different stages. So at some point you can probably imagine that just after the explosion, then we very likely are going to be in compression, okay? Beginning of compression phase, piston push on the ring, pushing on the pin pushes on the conrod, goes down, and there will be some resistance, at least at the beginning, from the journal in the crankshaft. Okay, so there'll be a state of compression at some point, just when the valves are open, the exhaust valve is open, then the piston is at the bottom and will go up and will be driven by the piston, the vacuum forming, and there is also some inertia going on, so there will be a state of tension. So we are going to focus. So to do a proper analysis, we would have to focus on a full cycle, so the 720 degrees, 2 revolutions of the crankshaft, and so on and so on. But here we are looking. This is not what we wanted to look at, especially. We are mostly concerned about meshing issues and things like that. But still, it's important to understand that there are some subtleties and complexities involved with loading conditions. So to simplify, we could decide to say, okay, right, well, it's very similar to tensile testing. So basically, where we could put that conrod into a tensile testing machine and load it as close as possible to the real state, and put some journal here, a pin here, and pull on these, and the journal and the pin act through these rings there. Okay, so we could try that. And what would that give? Well, that would give. Let's do it. So let's insert force here and force there, and no constraint. So to do that, well, you go to static structure, you insert your forces. Okay, just kind of without having thought too hard about it. No, the vector can work, but it can be a pain. So let's turn it to component. Oh yeah, let's select the face. So on the act force and along the X component. Now let's say there's a 4 kilonewton on the full piston. We have cut it in 4, so it will be a quarter of it, right? And the 5 kilonewton. So let's say 5 kilonewton. So divided by 4, 1, 2, 5, 0, and it's going towards the left or minus. And of course I put it in the Y direction, which is stupid. It should be in the X direction. X, and put it into the X component. One day, 0 is there. Okay, and that's one force. Let's insert the opposite force, balancing force. Let's see the force, and I could use vector and select a direction, but it's sometimes fluffy. Component is more freedom. Sometimes it's easier to type things than clicking. Okay, selection, of course, need to select it. Select the face. So select, and it looks like here. I'm being quick and I'm not thinking too hard here. All right. And what do I want to visualize? I would like to visualize the deformation along the x-axis x-axis, it's fine. And I would also want to see the stress, but the normal stress, so the standard stress we can calculate very easily, along the x-axis as well. X-axis. Okay, cool. I'm going to select these two, shift-click, right-click, and rename them with a definition. It can be if you have got more than one direction, it can be handy. Great, let's solve. Hey, it's solved. So, what have we got? Deformation, okay, very small, very small values. It's in millimeter. This is made of steel. Okay, fine. And what have we got? And the stress. What I was interested in is the stress. Okay, 175 maximum. What is that? Let's put it maximum. Yep, minimum, grand. As well. Okay, a bit of compression here, not much, and a bit of tension here. Fine. Okay. Now this is true scale. So you can't. It doesn't look like too deformed, which is fine. So it's not auto deformation, but the stress still is quite large, 175 megapascal. Is it really the real value? Don't know. I haven't carried out any proper analysis there, so I need to be a bit more careful. We need to do a convergence study, obviously, to be on the safe side. But yeah, it's relatively promising. What's interesting is that the stress in this area is a lot larger than in the other area. Capital probe here, 110 maximum at the root, as interior. Something interesting there again. Oops, very good here. 7, so significantly lower than here, and it doesn't look like there are any stress singularities just to the shape of it. Can't be guaranteed, and I would need to prove it by convergence study, but it should be fine. So what that tell me? What that tell me is that okay, that's interesting. Except all this is for the birds, because forces are the wrong type of loading. If I was using a tensile machine to load, tensile testing machine, an Instron, to load that con rod, as we explained, well, there will none of the force would be on the inside here, the big one, or inside of the small one. All the force will be pushed on these. And the way a force boundary condition in ANSYS is applied is each element has an area, and we'll have applied a proportion of the 1.25 kilonewton I had applied. So there are some loads here as well, but that's not what would happen in a real case. So something is not right, and I made a mistake. I should not use forces. I should use something else, which is more adapted. So I'm going to delete these two forces, and I'm going to insert instead a so-called bearing load. There's a bearing load. There's a little drawing, you can see, and it is ideal to represent the forces on the inside of the cylinder. So, okay, let's do that. Bearing load 1, the usual, yes, in the geometry, magnitude, vector, component, x minus 1250, and another one. Now, in case you want to learn more about how it works, you can highlight that and do a F1 to go straight into the website that does the help for ANSYS. I want that here. I invite you to have a look. It's not that informative on this one. Okay, another one. And the bearing load number 2 here. Geometry. I will do it by vector for a change. For illustrating it. So the direction is wrong. So I need to select the direction, click to change. Select that one. Wrong direction. So please change it and apply. There you go. Okay, so I have got my two bearing loads. Something I forgot to mention is that I don't have any fixed boundaries here. So I'm relying on the fact that the system will balance out the forces, and that is a bit chancy. Most cases it won't, and there will be a mistake. And so to be sure, there's a setup that need to be turned on. That's called weak springs. We discussed that already, I think, in week 2. But something to if you don't have a fixed boundary condition or a series of these, it's a good idea to turn on the weak springs. Okay, so that's done. Let's do it. So, which I had done before. I forgot to turn it off and on again. But by default, it's off. So what they do basically is they apply some very small spring at each node to essentially drown out numerical errors due from slight imbalances in the mesh, and so it's a nice way to get rid of numerical errors, very small ones, but which basically makes the part drift, and that would not be good. Right. Okay. So these warnings are due to the fact that there is no fixed boundary conditions and so on and so on. Okay. So let's have a look at the deformation. Okay, still very small, and stress. Whoa! Maximum stress 350, and guess what? We had 175 with normal forces applied. So you can see that instantly by applying incorrect boundary conditions or overly simplified boundary conditions, it's possible to make massive mistakes, and there is no way that and that error, factor 2 error, and that's obvious it's factor 2 actually, because as I was into that, the force is allocated. There is a traction, so a surface force allocated to all elements, all faces of elements, while the bearing load is still a force, but it's allocated only in the direction where the force is going, so that nothing on there, and predominantly towards the middle. I think it's called an elliptical. It has an elliptical distribution, so not so much here, more here. And so there is nothing. So essentially, there is twice as much force, if you want, going in the right direction than we had with the previous loading. So that makes a massive difference, and that needs to be identified. Otherwise, well, you can have a superb mesh, super well refined, still gonna be rubbish. Okay, so that's one thing. Something else that we can spot is that indeed it's still going to be everything happens here. All the action is there, nothing here. 225, yeah, way below. So something else we could do is, well, decide that we are not going to bother with that end and replace it by, so first of all suppress it and replace it by a fixed support. If I do that, I solve the proper fixed support. What do we get? We get, well, the following stress distribution. So the maximum value is 350 again. And on the other hand, what's happening here? Well, absolutely nothing. Because this is a fixed support. It's as if this has been superglued. That's the technical term. No, it's just nothing. Everything is fixed there. It cannot move. And the force is only towards there, so it's not going to affect it very much. Something that's quite interesting, though, is perhaps to double check that we are doing things the right way. Is to, if you have got fixed support, I would always recommend to insert a reaction, so that you can find it in the probes, and it's in the force reaction, and usually you locate it. If you have got some boundary conditions, you can have some fixed support can be called. You can do it by geometry, but if there is fixed boundary condition, you might as well call it directly. Okay, and solve again. Should be relatively quick. And what do we get? There's an element of symmetry here, but the total value at amplitude will be 150 along x. And there are also some elements in the in the y and z due to the symmetry, because the shape is not symmetric along that way, but not with respect to that axis. Okay, but what matters is that we put 250 in x in that direction, and we get it back on the reaction. So why would we want to actually replace our the load here by a fixed support? Well, that's because it's going to allow us to do more things, to add even more realistic loading conditions, and especially an acceleration to account for the inertia of the conrod.